Hi everyone. Thanks for coming. This is the introduction to game development talk. So originally this was planned to occur before we accepted new members, but we were having a lot of issues with like room booking and stuff like that. So we figured it's better to have it later than just to not have it at all. So here it is, I guess. So before we get started, for those who don't know who I am, I'm Michael. I'm a U3 software engineering student here at McGill. I previously entered at Ubisoft as a graphics programmer on For Honor. And I've just been really into graphics and engine development for a few years now, kind of as a hobby. So the way I kind of structured this talk was I tried to think of the questions that I had when I was first getting into game development. And I tried to basically structure this talk around answering those questions. So some of the questions that hopefully you also had when you were starting was, what is a game engine? Most of you have used Unity at this point, so you might have wondered, like, what is this application that I'm using? What's the purpose of it? And how does it differ from like the actual game that ends up being produced using the game engine? Also, I was kind of wondering, like, what are the systems that make up a game? Like, how do these systems interact and stuff like that? Some of you that were using Unity probably ran into components. So you might be wondering, what are components? Why do we use components in game development? So that idea is called like composition. So I'm going to be going over what composition is and why it's preferred over inheritance in game development. If you don't know what those mean, don't worry, I'm going to be getting into them later in the talk. And I'm also going to be going over a bit of math that you should probably know if you want to get into game dev. So first question, pretty cheesy slide here. What is a video game? So, I mean, all of us have probably, I hope, played video games. But I actually had a hard time making this slide just because it was pretty hard to kind of like actually explain what a video game is. So according to Wikipedia, a video game is an electronic game that involves interaction with a user interface to generate visual feedback on a video device, blah, 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 on a screen. I think that's a pretty good definition. I think like the main aspects of that I kind of take from that though is that a game has to be real-time and responsive, and kind of as a result has to be immersive. Immersive is kind of getting more into the design aspects of it, but it's good to kind of be aware that all the technologies and tools and systems that we're going to be developing are there to support a real-time and responsive environment, right? Also, one thing I should note is this is technically like an hour-long talk, but from like doing it, like practicing it, like it definitely does not stretch to 1 hour. So there's a lot of time for like discussion and questions. If you have questions at any point, like don't be scared to like put your hand up and we can talk about it. So I'm going to be kind of defining some like common game dev terms just before we get started. Right, so most of you have probably heard these words before, like a scene or entity or component, but I just want to kind of define them just so we just so we're like kind of we're on the same page before we move forward. So most of you have probably seen the idea of like a scene in Unity. Basically, this scene, some engines call it like a game world or whatever. It basically just represents like the virtual universe of your game. So the scene contains all of the entities that are in your game, where an entity or a game object is what represents a single object in your virtual game universe. So, a car is an entity, a person or a chair is an entity, etc. And each one of these entities can have a bunch of components associated with them. So a component basically represents some specific functionality or behavior that entity can have. And basically by adding a bunch of these components to an entity, the entity has all the behavior of all of the components that are attached to it. Are there any questions about that before? Kind of important thing to grasp. Most of you have probably seen this from doing the intro tutorial or whatever games you've worked on. Right, so getting to the question, what is a game engine? So put simply, a game engine is just a piece of software that's just a collection of tools and technologies and systems that you can use to develop a game. So most of you have heard of Unity. I mean, probably all of you used Unity for the intro tutorial, but some of you have probably also heard of like Unreal. There's a bunch of free engines. These are the most common free engines out there. Free for personal use, of course. If you actually end up making money from the game, you do also have to pay them a chunk of your money, of your profits. So a lot of like large AAA studios end up actually making their own in-house game engines. So Ubisoft, EA, Bethesda, they are all developing. They all have a dedicated engine team that is working on their own specific in-house engine. Does anyone maybe know of any AAA game engines other than Unity and Unreal? Just out of curiosity. Source engine for Valve. Nice. Yeah, so like Ubisoft, for example, has like two main game engines that they have. They have Anvil, which was the one that I was working on that's used for Assassin's Creed and For Honor. And there's Dunya, which is for Watch Dogs and Far Cry. Yeah. Yeah, they definitely do have. The name of it is escaping me. Maybe. That's a good question. I actually don't know. I feel like that's something I should probably know. But they definitely do have like a specific game engine that they're using for Fallout. Yeah, so like one thing to note is that Unity and Unreal is kind of targeted towards a very broad range of developers. So the idea is that you can really kind of develop almost any game, almost obviously being the key word there, any game in Unity and Unreal. It's supposed to be a very general and broad game engine, whereas in-house game engines made by AAA studios are very specialized to the kind of gameplay experiences that they're going for. So for example, like you definitely couldn't develop Assassin's Creed in Unity, for example, just because like the amount of like specialized technology and systems that they've developed just wouldn't lend itself to being developed in Unity.
This is
Creation engine for Bethesda? Nice. Okay. Was that also used for Skyrim, or is it just Fallout? Nice. Okay. Cool. So some of you might also have been wondering, like, do you need a game engine to make a game? Like, is that a necessary requirement? Is that like how it's done? Like, do people develop an engine and then use the engine to develop a game? And the answer to that is just no. I mean, like, it's very possible to make a game engine without using an engine. And this was actually used for a very long time, like before like engines weren't around at the very start of game engine development. Like it was very common for like the early ages of video game development for just to make the game completely from scratch. In fact, like the game Doom, which maybe some of you have heard of the game Doom by id Software around 1990, was the very first, like one of the first games where a clear separation between the engine and the game was actually being created. So at that time, the lead programmer for id Software, John Carmack, who's now like the CTO of Oculus, he's like a huge deal. So at that time, he was actually working on like a standalone engine. So they had a dedicated team working on the core systems, and then they had a different team that was actually using those systems to develop the actual game. And that kind of abstraction between the systems and the kind of game logic and assets allowed other developers to kind of mod the game and make spin-offs of the game using those core systems. So that was kind of the first time like the idea of a game engine was actually introduced. But if you are to make a game from scratch, like really from the definition of a game engine, all it is just a set of tools and systems that you can use to make a game. But there's nothing stopping you from building those tools and systems by yourself, right? But at a certain point, you're kind of reinventing the wheel, and especially for like indie studios, it's very just more common to use Unity or Unreal. But if you were to make a game from scratch, usually the rule of thumb is that whatever code that you're using, that you're reusing from project to project, is like the game engine that you're making. So you might be like making a game and just focusing on making a game from scratch, but like whenever you go to like make a different game, whatever code that you end up reusing is the game engine that you're developing. So this diagram here, which I took from Game Engine Architecture, it's a book about game engines. Basically, like the idea is that there's like this, on the very left you have cannot be used to build more than one game. On the right you have can be used to build any game imaginable. So you can imagine that like the more specialized the game is, the less code there is to be reused. Like for example, Pac-Man, if Pac-Man's your first project and then the second project is some like open world 3D game, there's probably not a lot of code that you can end up reusing. And then on the very other side of the spectrum, there's definitely no piece of software that you can use to make any game imaginable, like I was mentioning before. And then modern game engines kind of fall somewhere in the middle. Okay. Are there any questions about so far game engines? Unity would probably be somewhere close to Unreal. Unreal and Unity are pretty much the same. Yeah. That's a good question. I have no idea. I think for indie studios, it's small enough that like it's worth the cut versus spending a bunch of development time actually making your own engine. But it's high enough that like AAA studios do not even touch it. Yeah. I would imagine like 10%. I don't know. I'm not a bad person to ask for that. Oh, okay, nice. Yeah, I don't do game dev for the money. I do it for the passion. Yeah. All right. All right. So we're gonna be talking about a concept called the game loop. So the game loop is something that is in every single game, in every single engine. It's something that you just can't escape. It's very fundamental to the idea of what a game is. So again, from the game programming patterns, from a book called Game Programming Patterns, there's a quote: "Game loops are the quintessential example of a game programming pattern. Almost every game has one. No two are exactly alike, and relatively few programs outside of games use them." So basically, when it boils down to it, the game loop is just literally just a while loop. Like I'm assuming most of you have seen a while loop, or will eventually see a while loop in your intro to comp sci class. So it's literally just a loop that's iterating over and over and over again while the game is running, and your entire game goes inside there. So the usual like step-by-step process in the game loop is that we first start with processing input. So whatever, basically reading what kind of buttons or keys have been pressed. And one thing to note about that is that it's non-blocking. You're reading the input in a non-blocking fashion. So what that basically means is that the program isn't waiting for you to press something. The program is simply just like saying at this instance in time, what buttons and keys are pressed. Because again, we want to be going through this while loop as fast as possible. So we don't want to be stalling and waiting for anything, right? After we've received the input from the player, we basically update everything in our virtual universe. So you can imagine this as progressing the universe forward in time by a little bit. So a bunch of stuff can happen here. So for example, like using Unity, you've probably seen like the update method. That's one thing that could be done here. So for example, the update method could loop through all of your entities, loop and update all of their components, for example. Or it could like step some physics simulation, or it could like send some packets if it's an online game. I don't know. Like there's a bunch of stuff that can obviously go on here, but it's basically progressing the game by a single step. And then finally, we just render the game in the new updated state. So then we display that onto the screen. So this is happening all the time, and basically one iteration of this loop is one single frame. So that's where we get the idea of like frames per second. So if you're running at 30 frames per second, then we're iterating through this loop 30 times in a second. One thing that's kind of missing here that maybe some of you have noticed, is there something that like is wrong here that anyone can pick up? Yeah, in this specific case, yeah, it's well, true. Let's assume that it says like while the game is running. There's still like a pretty big issue here. Yeah, that's definitely true. Usually the setup occurs before, so like I didn't include that here, but there's like all the initialization of all the systems occurs first, and then we have the loop. But generally the main issue here is if you can imagine like we have like a super fast computer and then a super slow computer, right? If we have a super fast computer that's maybe iterating through this 30 times a second, and we have a very slow computer that's doing it like maybe 5 times a second, like since each iteration of this, maybe you have an idea of what's going on? Exactly. That's exactly what we're getting to. So like if we're like literally stepping here, like there's no notion of real time here. Like real time as we perceive it. Like this is simply updating as fast as possible. So on a fast computer, if we step this 30 times versus on a slow computer that we step 5 times, the game will literally be going faster on the faster computer. Like if we have a car that's moving, for example, on the faster computer, the car will actually be moving faster than on the slower computer. And obviously that's we don't want there to be discrepancy in gameplay between the speed of the computer. Is there any questions about that? I feel like I maybe didn't explain that great enough, but everyone's on the same page. Great. So this basically gets to the idea of frame independent motion. So in Unity, you probably saw the whole like delta time thing, where whenever you have some kind of translation or rotation, you're always multiplying by delta time. And basically that's to ensure frame independent motion. So essentially, if you look at this new game loop that we have, we're essentially grabbing, at the beginning of the iteration, we're grabbing the current time, and then we're calculating the elapsed time. So basically the time that it took to render the previous frame, or the previous iteration of the while loop, and we're passing that into the update method. So what we're basically doing is, instead of just updating like a fixed amount every iteration, we're actually updating by the exact time in the real world that passed during the previous iteration of the while loop. So coming back to the analogy of like a fast computer and a slow computer, in this case, like if you imagine like a bullet, for example, crossing the screen, in the fast computer that's doing like 30 frames per second, for example, we would have like 30 little ticks, right? On the slow computer, we would have like 5 ticks. But the reason, the difference here is we're actually scaling the amount of the distance that the bullet is moving by how much time was elapsed. So on the fast computer, we would have 30 small ticks, whereas on the slow computer, we would have 50 larger ticks, because the delta time is larger, because it took a longer time to iterate through the while loop previously. So the end result here is that the bullet will end up, after a second, it will end up in the same location on both computers, even though on the fast computer we iterated more than on the slow computer. Is that clear? Any questions about that? It's kind of like, basically, to boil it down, to make sure that the experience and everything is running the same on every computer, we must multiply by this like elapsed delta time. Yeah.
How does the time not overflow
Too big of a number? Like if elapsed is like an extremely large number? That can definitely happen. Like if we have, say, because this is like the elapsed time of the previous frame, right? So if for some reason like we get like a huge spike in usage and update, like some giant like explosion just went off, right? And it took like an extremely large time to calculate that, and elapsed is extremely large. Sure, like the frame is the idea is that the frame might be lagging, like our frames per second might be lagging. So at that, like our frames might drop to like 2 frames per second, but we're calculating the elapsed time and passing it to the physics simulation. So like if 1 second passed, it's like some extremely large number, the physics simulation would still like go like step by that delta time. So in that case, like say like where we only iterate through it once, the elapsed time is extremely large, and then in the analogy with the bullet, it would just like go from one side to the other immediately. I don't know if that was a great explanation. Did that kind of answer your question? All right, so that is frame independent motion. So we can finally get into the systems that comprise a game. So one thing that I really like about game development is that there's just so many systems and like fields of computer science that go into developing a game. So like no matter what you're into in terms of like computer science, there's like always something that might interest you in game development. So the big systems that comprise a game are like the graphics system, animation, physics, networking, audio, and there's a bunch of different other systems that I haven't mentioned here, like I don't know, resource management, debugging, profiling, whatever. But the systems that I'm going to be specifically talking about are the graphics and the physics system, just because I don't really know a lot about the other systems. So, right. Not to say that the other systems aren't as important. It's just like, obviously, I'm only going to be talking about the things that I've experienced. So this is like a scary picture that I took from also the game engine architecture book. So this is kind of supposed to outline like the potential systems in like a modern AAA game engine. So there's a lot of stuff going on here, and like it's no surprise that like if you look at any kind of like web page that lists projects by like lines of code or something. Like modern game engines are like very, very up there, like in the hundreds of millions of lines of code potentially. So this diagram it starts from like the lower level. So we have hardware. As we go up, we get higher and higher, more abstract, until we get to like the game-specific subsystems at the very top. But you can mention, you see here like render. There's probably physics somewhere in there. Debugging, yeah, physics here. But there's a lot of systems that go into game development, and I encourage you to maybe look at this slide later and maybe see if there's something in here that you're more interested in, kind of explore that field. Also, you might have noticed that this is a very like kind of programming oriented talk. I really apologize if you're not into programming and you're into like art or something. But like this definitely is supposed to be useful for you as well. But obviously, I'm coming from like a programming standpoint, but I'm going to do my best to kind of give this introduction to like all kinds of fields. Yeah. The very top one is game-specific subsystems. So these are systems that are developed for the game specifically. So, for example, like Unity might be like all of this here, and then when you make a game in Unity, you're probably going to develop weapons, develop power-ups for that specific game, and those kind of fall under the game-specific systems. Okay, so this is kind of like a cool hype video that I don't know. I thought I would put it here. It's about graphics. There was like a really cool music video or audio, but apparently that's not working. I think, yeah, it messes up like the mic though. Maybe I can change. Hold on, I really like the music, so I'm gonna try try to figure this. Huh? No, wait, hold on. Let me try to fix this. I can probably just like change the sound settings. Yeah. Yeah, so this video is from Substance, and they basically make, I think they make a bunch of like texturing tools. It's probably gonna be terrible for the recording. I think we get the idea. Graphic system. So this is like, I think the coolest system. Probably a biased opinion, but the graphic system is basically also called the renderer or the render engine. Is basically the system responsible for drawing the final frame onto the screen. So in the game loop that I showed earlier, this is the system that does the render function method at the very bottom. So essentially, like if we come back to the analogy of a game having like its own virtual universe and a bunch of like objects in that virtual universe, you can imagine like, obviously if I have like a camera and I take a picture like in this universe, what's happening is like there's a bunch of light bouncing off all these objects, and they're eventually reaching the lens in my camera, and they're reaching like the sensor in the back of the camera, and then I'm creating a picture. I don't know how cameras physically work, but it's something along those lines. So you can imagine like the render system is just like you have a virtual camera in your virtual universe, and you're taking a picture, or rather, I guess, a video in this virtual universe. So the graphic system basically is responsible for taking all these virtual game objects in your scene and somehow translating that into colors of pixels onto the screen. So this was developed. This system is usually developed by graphics programmers. Right. So in the real world, we're all like physical objects. Like we like interact and reflect light and do a bunch of cool stuff. But in a game, like there's nothing. All the entities are not like they're virtual. There's no tangible object to reflect light. So all these things need to be simulated. So the render system has to have like some kind of visual representation of the game object. It needs to be aware of the game object. So this is usually, there's three things that usually comprise like the visual representation of an object in the scene. Usually the triangle mesh, which is basically the geometry of the game object. So this sphere here is a triangle mesh. of a sphere, basically just like a bunch of triangles connected to each other. There's the material, which basically describes how the object interacts with light. And then there's the shader, which is just a program that runs on the graphics card that will actually take the triangle mesh and the material and then produce the pixels onto the screen. Right, so each triangle in this triangle mesh is made up of 3 vertices. And then basically each vertex has a bunch of attributes that describe the vertex, like position, normal, a bunch of stuff that basically tell the graphics card, along with the material, how to actually produce the pixels. Obviously, like this is a gross simplification of what's actually going on, and I'm not gonna super dive into it, but just know that basically, like in your whatever engine that you're using, like Unity or Unreal or whatever, you have like the object, and like I think in Unity it's called like a mesh component or something, but basically you have some kind of like representation that the graphics system sees. And that's what ends up being displayed onto the screen. So on the next slide here, I have like some examples of triangle meshes. I mean, really, like if you have an infinite amount of triangle meshes or triangles, and like an infinitely skilled artist, like you can technically simulate like any object, any possible object. But pretty cool stuff. But you'll notice here on the bottom right here, there's a bunch of spheres, which like probably have the same triangle mesh, but you'll notice that they all look different. And that's to do with the material and the shader that's attached with that game object. So the material and the shader basically describe how the object interacts with light and how it should be displayed onto the screen. So we can get a bunch of cool effects from that. So I know this was like a super basic introduction for the graphic system, but like just the things to kind of take away from this is like, again, each entity has a visual representation. That representation is made of the triangle mesh, the material, and the shader. That's kind of what you really need to take out of it. I have another hype video for physics, although physics isn't. I don't know. I just literally looked up physics in video or something. You guys kind of get this. Other cool stuff. So the physics collision system. These kind of are different systems, but they're usually clumped together. Physics and collision. So the physics system is essentially like the system that's supposed to simulate physics in your game, right? So like in the real world, we have physics, obviously. So again, this virtual universe, there's no like laws of physics. You have to create the laws of physics. And that's kind of what the physics simulation does. So in this simulation, like every game object is like an actor. Like in like physics engine literature, they call them like actors in the simulation. So you have a bunch of actors, and they're somehow interacting with each other, bouncing off each other, colliding with each other, applying forces to each other, whatever. And the physics system is basically the thing that handles that entire simulation. So I mentioned before how there's a visual representation of the game object, which is kind of like the mesh material things that I mentioned before. But those are fairly complex. Like if you have a complicated mesh, it's not like super obvious how to like detect collisions between these like complicated meshes, right? So usually we use an idea of like a collider. You probably experienced this in when you're using Unity for the intro tutorial, maybe. So the collider is basically like the physical representation of the game object. So the mesh is what the renderer sees, and the collider collision body, whatever you want to call it, is what the physics system sees, or what the physics collision system sees. So this is obviously like most of the time this is a gross simplification of what the actual object looks like. So Unity uses like square, cubes, spheres, and capsules. And the reason behind this is really just because detecting collision between these simple objects is much easier than detecting collision between like complicated mesh objects. Yeah. Yeah, basically, like, yeah, exactly. So when you're saying, like, when, I don't know, I guess, well, the thing is, like, these colliders are fairly simple, but I guess, like, if you actually have a game that's, like, the collision, like, the hitboxes actually really matter, you can have more complicated colliders. Like, you can actually have a mesh collider, like, that completely perfectly wraps the mesh. But obviously, the more complicated the collider, the more pricey, like, the detecting collision is and stuff like this. One thing that is also commonly used is, like, you can actually, like, build multiple, like, build more complicated colliders using more simple primitives. So, like, you can, for example, like in this picture, you have a tree, and they have, like, a bunch of different colliders onto them. But one thing you can also do is, like, have a capsule collider for the trunk and, like, a sphere collider for the branches or something like this. So there's ways to get creative with it. All right, game dev topics. Before we move on, are there any questions about anything that was covered so far? No? I just want to... Oh. Yeah. Yeah, exactly. So you can, like, I think they're called, like, I forget what their name is. Well, I guess, like, the mesh collider would be, like, you would actually use the mesh data to generate a collider. Well, like, I think they're, like, called, like, composite colliders or something like this, where you basically just, like, imagine if you had, like, a skeleton, a person, you could, like, combine a bunch of spheres or something to make one big collider with the spheres. Any other different questions? Oh, okay. Right, so getting into inheritance now. Does anyone not know what inheritance is in object-oriented programming? It's okay if you don't. It's like this is a completely beginner-friendly class. Okay. I'll discuss inheritance a little bit then. So inheritance is basically an object-oriented programming, like, feature tool, where basically if you have a class, you can inherit from that class to create a subclass, which basically has a copy of all the functionality of the parent class. So basically, like, one example is, like, if you have, like, a system class that has a bunch of, like, basic system initialization, I don't know, whatever, and then you, like, inherit from that class to create, like, a render system, for example. That way you gain all of the functionality that the system class that you inherited from implemented, and then you can have more specific functionality for that specific render system. So it's basically a way to, like, reduce duplication, and kind of just it's a better way to kind of manage and structure your application. I don't know what's going on over there. So this seems like pretty great in hindsight, like, just looking at it, like, oh, this is amazing. Like, you know, I can have this, like, crazy hierarchy of classes, and I don't need to write code a lot, and this is great. But, like, this is very, like, dangerous in terms of game development, and I'm kind of going over why in an example. So this example is also taken from Game Programming Patterns. I also, like, again, highly recommend looking at this book. It's completely free online, and it covers, like, a bunch of very, very useful information. So this one is called Game Programming Patterns, which I took for this example from, but there's a Game Engine Architecture is also a really good book, but it's definitely, like, it's like 2,000 pages. It's, like, basically the Bible of game engines. But this one's, like, a very more easy, like, beginner-friendly, like, it's like a very good introduction to general, like, design, game design. So let's suppose that, like, for example, we're making a game from scratch, and we want to have game objects in the game, obviously. So we make a game object class, for example, and we put some, like, game object initialization code in there. And now we come along and we want to make, like, a decoration entity that, like, it doesn't, like, collide with anything, but, like, it can be rendered. So we create the decoration class, we inherit it from game object, and then we write some rendering code that, like, will display our decoration class onto the screen. So that's cool, that worked. So now let's make a zone class. So let's say a zone is, like, an invisible thing in our game that can detect when another entity collides with it or gets into the zone. But it's not, like, actually something that you can see, it's invisible. So we again create the zone class, inherit from it, from game object, write some collision code, everything's good. The problem arises when we want to have, let's say, another game object called like prop that has both collision and rendering code. I'm also assuming single inheritance here. I don't know if that, like you can only inherit from one class. Multiple inheritance is like a whole other thing, but the issue arises here because, if we inherit from the zone, if we inherit directly from game object, then we're gonna have to be duplicating rendering and collision code, and we've kind of just skipped the whole point of using inheritance because we haven't used other code that we implemented in other classes. So if we try to inherit from zone, like we get the collision code, that's cool, but we don't get the rendering code that we just implemented in decoration. So we need to now duplicate rendering code. So we really only gain functionality from the direct parent class, or in all the other parent classes, but from the parent class that we inherited from, right? So you can imagine that if we have a bunch of different game objects in like a more complicated structure, that there's going to be a lot of code duplication here, and it's really just not scalable. Like it's the idea of like one thing that helps in games is like iteration speed and being able to kind of like be flexible and add new features fast. And this definitely does not lend itself to that. This is very much of a headache. Like, do I inherit from zone? Do I inherit from decoration? Like, what do I do here? It's not very clear. Does anyone maybe have an idea that would maybe mitigate this a little bit in this case by still using inheritance? Can you repeat that? Sorry. Yeah, I mean that's definitely a good solution. The only problem there is that now zone has rendering code and rendering data, and decoration has collision data, right? So it's definitely like the best way of doing it in this case, but it's still not. That's why inheritance is bad, basically. In this context, inheritance is great in other aspects of programming, but not in game dev or game programming with entities. So this is basically what I just said. We're forced to duplicate code since we don't, we can only inherit from one of these game objects, and it's not very scalable. So the solution is composition. So composition is basically a different mentality when it comes to object-oriented. It's like another, I guess, paradigm you can call it. I don't know. But basically the idea is that instead of having the functionality be directly in the entity, we'll implement the functionality in a component class. And then we'll have the component be within the entity. So in the previous example, when we had rendering and collision, we would have a collision component that has all the collision code. We could have a rendering component that has all the rendering code. And then the entities are now just basically, all they have is just a list of components that are associated with that entity. And now there's no code duplication because we just make the rendering component once, and then whatever game object that we want to actually have displayed on the screen, we just add the rendering component onto it. Whatever object that we want to have collide, we just add the collision component onto it. So this is a very, definitely a better system, and it just makes more intuitive sense, right? If you view a game object as something that can change and is dynamic, it makes sense to kind of be able to pick and swap components from the entity. So I think these points kind of just repeated what I was saying. I guess, yeah, so pretty much every modern game engine uses the approach. I'm sure using Unity, you've worked with components. Unreal also probably, I've never actually used Unreal, but they use components. I know the game engine at Ubisoft also uses components. So this is definitely something that you should understand, and this is kind of, if you're ever wondering why Unity uses components, this is basically why, because the other solution of using inheritance is not, there's a lot of issues with it. Are there any questions before? I think the next slide is math. So any questions about composition?
Is it the same as polymorphism?
Polymorphism is the idea of it lends itself to inheritance. So with polymorphism, poly is many. The way I see it is poly is many, morphism is changing. So I think with polymorphism, the idea is that if we have a game object instance, that game object instance could actually be an instance of a zone class. So like, it's not the same idea, but like basically it's the idea of like a child class can be pointed to using a pointer to its parent class. And it can kind of change that way. Any other questions? Math. All right, so math is very important in game development. Specifically, linear algebra is pretty much the more important of the maths that you need to know. So, you know, it's kind of like natural that like if we have like a 3D world, you know, or even a 2D world, but I kind of like to talk about 3D. Pretty much everything in the 3D world is going to be represented using vectors. So, you know, the position of the game object is going to be given using vectors. The direction that the object is moving is going to be given using vectors. So, naturally, the field of linear algebra is very useful when working with game objects in the scene. So, something that you should probably know is vector arithmetic. So, I think, have any of you like not taken linear algebra in freshman year? Okay, so this is probably a lot of review for everyone, but it's very important to kind of know the basics. So, yeah, vectors, I already mentioned that they can be used to represent position and velocity, but they can also be used to represent other things, like the direction an object is facing can be represented using a vector, or the normal, which is basically just like the vector that's perpendicular to a surface, is also represented using a vector, etc. So basically, yeah, I'm not going to like go over specific details, but you know, if we add two vectors together, we get the summation of the vector. Subtracting two vectors together. These are dot product and cross product are kind of just tools that you just really need to really understand and have like an intuitive grasp of them, because they're used a lot in game programming. So, you know, dot product is the a projection of one vector onto the other, the magnitude of that one vector projected onto the other, and cross product is just basically a way of getting a vector that's perpendicular to the two other vectors. So maybe a better way of doing this is to give like a specific example. So let's say like in the introduction tutorial, for example, like one of the bonus tasks was making a turret. So let's say you want to make like a turret that, you know, it has like some muzzle, so it has like some direction that it's facing. And then we want it to, once the player gets into some like field of view of the turret muzzle, and we want to automatically like lock onto the turret, for example. So how would we detect that the player is within the field of view of the muzzle, right? So we're given the position of the player, we're given the position of the turret, we're given the direction that the turret is facing. So now we just need to do linear algebra. So I have like a very, very complicated drawing I made in Paint yesterday that illustrates this. So we have a position of the player, position of the turret. So if you want to find the direction that the player is with respect to the turret, we basically just subtract the position of the player using and the position of the turret. This is the subtraction part of the vector arithmetic. So now we have the direction that the player is facing from the turret's perspective. And then we can basically just use the dot product of these two vectors normalized in order to find the angle between the direction that the turret is looking and the direction that the player is from the perspective of the camera. And then we can have like some kind of minimum value where like if this angle is less than 10, then lock onto the player or whatever. So this is maybe, I hope this kind of gives you an idea of like how useful linear algebra is, and like how pretty much everything in games, any kind of gameplay feature, like anything, is using linear algebra. This matrix vector multiplication. This is something that I kind of hesitated in even including. Just because it's not even really used a lot, to be completely honest, in anything other than graphics. In graphics, it's used very, very heavily. But in gameplay, like usually, like the game engine exposes tools for you that you don't even really need to do matrix multiplication. But it's good to just even have like an intuitive grasp of what's going on when you're multiplying a matrix with a vector. So I'm sure most of you have seen this, like basically how to multiply a matrix with a vector. But there's two kind of ways of like interpreting this. So one way of interpreting it is that you're taking a linear combination of the columns of the matrix. That's displayed here. So this is a very useful interpretation of the multiplication if this matrix, for example, is used to transform the vector. So I'll be getting into another example with that before, but another interpretation that you can use is basically this is you're taking the dot product of the rows with the vector. So that's another interpretation. So these are basically the two ways of interpreting a matrix vector multiplication. The one that's probably most useful is this one. I usually like to think of it as a linear combination of the columns, just because it lends itself to most of the problems involved in game dev kind of lend itself to this kind of interpretation. So one specific, I'm going to be trying to do this. I did this very last minute, so hopefully I can explain this well. But one use of matrix multiplication is change of basis. So basically, commonly in any kind of 3D scene, we'll have different coordinate spaces. So if you can imagine like this room, for example, let's say like the corner of this room is the origin, and then all of our positions are given with respect to that origin, for example. And I could also have my own coordinate system, and all of you can have your own coordinate systems, where like the origin is like the middle of your feet, for example, and all of the positions on your body could be given to either that coordinate space or with respect to the room's coordinate space, for example. But now the question arises of like, if I have a vector given with respect to my coordinate system, how do I represent that same vector with respect to the room's coordinate system? And basically, this is a matrix transformation called change of basis. So one way of doing this is basically each coordinate system has like basis vectors, which was maybe covered in linear algebra. But basically, the basis vectors basically describe the coordinate system. So one way of doing a change of basis is representing, let's say this monkey coordinate system is space A, and this other system is called space B. So these are the basis vectors of space A. If we represent the basis vectors of space A with respect to space B, so here, let's say this is like, the standard, like x is equal to 1, z is equal to 1, y is equal to 1. But obviously in this coordinate system, that's not the case. So if we represent all these basis vectors with respect to this coordinate system, and then form a matrix where the columns of the matrix are those basis vectors represented with coordinate system B, then we get a transformation matrix from coordinate system A to coordinate system B. This is very hard to explain using this very one drawing and just me talking. But basically the main thing I want you to take out of this is like, this is like one of the main uses for matrix multiplication, I guess, in game development. So there's a lot of crazy cool stuff. This is kind of just scratching the surface, but you can really dive into linear algebra and math. That's also kind of why I like game development, because it's a mix of programming and math, and I think that's cool. I think that's basically it for the talk. Did anyone have any questions about just anything? Or if you just want to talk, say hello. No questions.
I saw that people are like making teams and stuff for games.
Yeah.
Do people form usually teams monthly for each of the challenges, or for the whole year?
Yeah, this is a question we got asked a couple of times. I guess the idea of like the monthly game jam was kind of confusing, just because like one thing I kind of want to make clear, I guess now that we're all here, is like the monthly game jam is not necessary. Like you can make a game without participating in the game jam. Like if you want to make your team and you want to make like a year-long game, you're free to do that. But the game jam was basically just used to encourage you, to kind of give you like an idea, like the theme, where you can like maybe kind of, it's like a catalyst for making a game. So you're definitely free to find like a team that you make a game with monthly, or you're free to make find a team to make a game, a yearly long game. Or you're also free to just make a game by yourself. Like there's no, as long as you're working on something with games, then it's all good. I think there's a question in the back.
Yeah, I just wanted to go back to the framework, you're limiting the time.
Oh yeah, sure. Right here? Yeah.
So you're specifying the time intervals every
The elapsed time that we're given here is the time it took to render the previous frame. So let's imagine like it's the first time we're going through this. So last time is equal to get current time, so it's the current time. Current is going to be the same as last time. So in the first iteration, it's just going to be 0. Elapsed time is going to be 0. But here at the very end, we're updating last time to be the time at the start of the frame. So then when we're in the second iteration of the frame, we're basically subtracting the previous start time with the current start time. Basically, yeah. So passing in however long it took for the previous frame to render. I guess one thing I can mention is this is not actually how it's done. This is just like super simple. I forgot to mention that. There's a note here. This has many issues, which I'm probably not going to get super into, but if you're interested in learning of how a more elaborate system, but how it's actually done in most game engines, you can do the Game Programming Patterns book. There's also a great resource. There's a game loop section there, so I encourage you to look at that. The main issue with this is that there's a lot of small steps. So imagine we have a super fast game and elapsed time is super small every time. So we're doing a bunch of small steps. The issue there is that floating point arithmetic in games, or just in general, floating point math is not very accurate. So if we're adding a bunch of these and accumulating a bunch of floats, the more we do it, the more error there's going to be from the actual real sum of all the floats. So what ends up happening is if we have a super fast computer or a super slow computer, since we're doing a bunch of floating point arithmetic on the fast computer, it'll actually, the final, if we use the bullet analogy, the final location of the bullet will actually not be the same, just because there's errors in the addition when we keep adding all those values. So the solution to that is to have fixed time. Again, I'm not going to super go into that. I don't even know too much about that. So if you're interested, go to this link wants to show up. Yeah, Game Programming Patterns.
But generally, it's a good practice just to fix the performance of that.
Yeah, I mean, for a basic example, this is a good way to kind of think about it. But if you want to dive more into it, there's a lot of better solutions for sure. Any more questions? Yeah.
Game loops single threaded?
No. In this example is definitely single threaded. But in most game engines, what ends up actually happening is each one of these systems usually has its own thread that gets updated, and all that complicates the game loop a lot, because if the render thread is ready to render, but we're still updating the physics system, what do we render in that case? There's that whole realm of multi-threading in game engines that I don't actually have a lot of experience in, but yeah, there's a lot of complicated and cool stuff that you can do for sure. Any more questions? Yeah, I think that's it then. Thank you guys for coming. I'll be here, I guess, if you want to ask questions, but yeah. Thank you.